Hello everyone. In this session, we are going to discuss about infrared spectroscopy. So uh, we are gonna discuss that what is the infrared and how we can detect the infrared and how we can understand the chemical formula or the groups inside the a composition. So you see that the difference between these techniques use NMR, IR, and mass spectroscopy and UV. These are very brief explanation of each technique, so you can make yourself familiarized with these techniques. And so we are going to discuss this session about the IR spectroscopy. As you know, IR is about the interaction of the infrared radiation with matter. So the information that we can take about the IR is chemical nature and molecular structure. So uh, what we do is that the IR is gonna be absorbed, and the vibration, uh, it makes a vibration, and there are some part of the IR that is gonna be transmitted. The detector is going to absorb that transmitted uh, photons. Here is the wavelengths and the frequency of the IR, and you need to note that the IR shows us the what type of bonds are present and some structural information. Uh, it is important to note that IR is not the only technique that you can do for showing the chemical formula or the groups. It should be in parallel or in addition with the other techniques to your identification. So we cannot just use this technique to make identification. You should know that. So as you see that the wavelengths of the frequency of the IR is shown, and it can cover a covalent band, stretching, bonding vibration, and so uh, you see that the stretching frequency is changing based on the atomic mass and bond energy. So as long as we are increasing the mass in the CH group, and then CD group, and then CC group, you see that we have a decreasing, but with the increasing of the band's energy, we have the increase of the uh, stretching frequency. And this is the same. You see that the frequency decrease with increasing atomic wavelengths, and frequency increase with increasing bond energy. So after sending IR, it makes it, it's a sort of thermal energy, causes a vibration. Bonds, it causes the bonds in molecule to start vibrating. So it's like it works like a spring, and after we stretch, it vibrates. So that's why we say that the IR is causing vibration. So see, you see that the IR after sending, it causes vibration. It absorbed by some groups and makes vibration in those groups. And then some part of that IR is not gonna absorb it. It's gonna transmit it. The detector is gonna detect those transmitted light, and then it shows us. So here you see that the absorption, we have it based on the wavelengths and the percentage of the absorption. In this slide, we have the wavelengths based on the transmission. It is the most usual uh, display of the IR spectroscopy, and you see how we should show the IR. And for the classification of the IR bonds, you see that we have three types: weak, medium, and strong. So usually the polar bonds like CO bonds, CO double bonds, we have a strong IR adsorption. For C triple N, triple bond with N, we have a medium adsorption, and we have a weak adsorption between terminal carbons. And usually in the symmetric formula, there is no uh, vibration and absorption. Infrared bands, uh, they can be sharp and they can be broad. So in this figure, a typical example of a broad band is shown to you is for the OH band in alcohols or carboxylic acids. You need to make yourself familiar with this type of broad band. So IR is most provide is the most useful in providing information about the presence of the or absence of a specific functional group. That's the best uh, performance that you can expect from the IR spectroscopy. IR can show you the molecular fingerprint, in the 600 wavelengths till 1400 wavelengths, 1400 wavelengths. It shows the fingerprint of each organic molecule. So IR does not provide detailed information that you should uh, remember, and the scope is really limited for the use of the IR. So here is the a brief display of the IR adsorption. And as mentioned, it can be used as a fingerprint in the range of the 600 to 1400. Here's another display of IR adsorption. You see that between 600 to 1400, you have the fingerprint of the molecules. But usually we take our observation above 1400 to 4000, so or 4000. Between this range of the wavelengths, we try to understand or recognize the chemical formula. So here is this schematic of absorption of the groups, the region of the spectrum where the following types of bonds normally adsorb. A sharp bond around 2200 to 2400 would be indicating a possible presence of the CN or CC. And as you see that between 600 to 1400, you have the single bond of the CC and CO and CN. Between 1600 to 1830, you have double bonds of the CC and CO and CN. And usually around 3000, somehow around 2700 to 3500, you see that the stretching of the CH and OH and NH. In following, we explain in details. So for the alkane, you see that we have the stretch of the CH around 3000. It shows some sparks very close to each other, and some bending for CH around 1400. But the one that you need to recognize is that the CH stretch around 3000. For the alkenes, as you recall, we have the stretch of the C double bonds around the 1600, between 16 to 1800. So that's the one that it helps us to recognize the alkenes. And also we have the weak stretch for the CH bond, for the terminal CH bond, around 3080. So that's the formula that you need to see how they are recognizing the this hexane. So we have a sharp and medium band uh, corresponding to C double bond, stretching vibration at the around 1600 to 1700, and also we have a CH uh, bond stretch appearing around the 3080. For these two for these two groups, we can recognize alkenes. For the alkenes, also you see if we have the cis uh, formula, you have the different stretching. And the most important things, because of the symmetric, further symmetric, we have the lower stretching of the CC double bond at 1660. That's that happened because of the some symmetric condition for the cis formula. And also you can understand the formula from the uh, stretch of the CH at 3000, around 3000. So for alkynes, the most important band is the triple bond between two carbons. We have a sharp, weak bond at 24, 2100. But we have a two condition. Either carbon is that as is shown as a terminal carbon or terminal alkynes, or we have internal alkynes. So for the terminal alkynes, we can see the CH bond vibration at 3300, but for the internal alkyne, there is no indication of the CH bond uh, around 3300. We only have the stretching of the triple bond between carbon and carbon. Here you can see the difference between terminal carbon or terminal alkyne and internal alkyne. That there is no CH stretching for the internal ones. For the nitrile, we have the stretching around 2200. For this formula, as you see, because you see that we have a stretching, a sharp and medium stretching around 2250. For alcohol, as we mentioned, we have a broad stretching for OH around mm, between 3000 to 3500. So for the uh, aldehydes and ketones, you need to remember that the aldehydes and ketones show a strong, prominent, and stake-shaped bond around 1710 to 1720. This band is due to the highly polar CO uh, mm, double bond. And we have, because the aldehyde also has also contain a CH bond to the sp2 carbons of the C double bond. We have another vibration around 2700 to 2800. Here are the display of IR for aldehyde and ketone. You see that both they have the prominent stretching, very sharp and strong, around 1720 to 1730. For For the aldehyde, also we have a stretching for CH bond, but that stretching for CH bond is not appearing for ketone. For carboxylic acid, also we have a broad stretching for OH, as you see, and also we have the stretching for CO double bond. For amines, you need to know that if that amines it has a two hydrogen or one hydrogen. If it has a two hydrogen, we have a double spike around 3500. If it has a one hydrogen or secondary nitrogen, if it is a secondary nitrogen, we have a one spike. If it is a primary, it is one two spike that we can see for the amines. And for amides, you would see one stretch, both stretch for the NH and uh, uh, CO double bond is going to be visible. A very strong, somewhat uh, broad bond at the left end of the spectrum in the range between 3100 to 3500 for NH, and around 1710 uh, we have for CO double bond. That's for amides. Thank you for considering this explanation. Hope you are doing good at your test. Thank you and have a good week.